Good afternoon and welcome back to the ESA Scout HydroGNSS online workshop. The next session is a follow-on session from the HydroGNSS mission and research topics. The chairs for this session are Peter Garner, Project Manager for the HydroGNSS mission, and Professor Nazareno Piedica from Sapienza University of Rome. Peter.
Thanks, Ben. Yes, welcome back, everybody. Nice to get started again after a break. So session 3 is going to be looking at the HydroGNSS mission details. You're going to hear from members of the HydroGNSS GNSS core team here at SSTL. So first to go is going to be Serena Donati. She is the Senior Systems Engineer and HydroGNSS Technical Lead, and she's going to be talking about HydroGNSS mission and systems. Serena, the floor is yours.
Thank you, Pete. Hello, everyone, again. I'm going to give you a presentation, as Pete just said, about the HydroGNSS mission, its main objectives, and also some details about the system design and the overall technical solution. So we've been saying over the past sessions that the mission objectives on HydroGNSS are developing, qualifying, and validating a space mission with the aim of generating GNSS reflectometry products, mainly targeted on land. And in order to do that, the spacecraft has an onboard science instrument which can provide process reflections, including what we call delayed Doppler maps. And this data is then downloaded to the ground station and converted into level 2 products. And these products are a description of some key climate variables. And if you were here this morning, you have heard about all those climate variables from our colleagues. So some of the key mission aspects, this mission is designed to support a lifetime of 5 years. And during this lifetime, the objective is to deliver reflectometry EO products to the science users. And that's based on ESA's free and open data policy. So that means the data is made available for free on a web portal, and any user can register on the portal and download the data over the internet. So what we provide with this mission is really a service to the end users, and we have a requirement in terms of availability to achieve a service availability better than 90%. So we can make sure we deliver a good quality service. The products that we have on HydroGNSS have quite a few novelties in terms of reflectometry techniques. So we have dual polarization, coherent channel, as we discussed this morning, and dual frequency as well. And because HydroGNSS mission is about the science, we have also some requirements in terms of scientific readiness level. So we want to make sure we can achieve SRL 7 by the end of phase 1. So that will be 6 months after launch. And then once the system is up and running and in service, we can further develop the science and achieve SRL 8 at the end of the nominal mission lifetime, which is 3 years to begin with. There is a possibility, as we said this morning, for an extension of the lifetime to take it up to 5 years from launch. To give you a bit of background about the Scout approach and basically the foundations of this program, the Scout program is the agency's response to ever-evolving scientific and technological environment in the Earth observation field. And the main objective is to reduce schedule and also contain cost to deliver scientific solutions to non-commercial applications. And in order to do that, we take advantage of some approaches like new development methodologies, but also controlled high risk. And a good example of that is the use of COTS components, which can be a key factor in reducing the hardware costs. SSTL is definitely a good fit for this type of mission because we work in a vertically integrated structure, and what that means is that we have end-to-end full capability in-house. We can design, develop and build components, avionics. We have in-house testing facilities to support qualification campaigns, but we also have very extensive experience in launch procurement and supporting launch campaigns, as well as dealing with the mission operations once the satellite is in orbit. So as you can imagine, having all those capabilities centralized gives us a very good control over cost and schedule and risk, which is really the key factor in the Scout program. But also we can have a better rebuild cost. So once we've spent the NRE at the beginning of the project, the repeat build is extremely low cost for successive satellite constellations. So we can potentially add on extra satellites in the mission, which will provide us a higher timeliness and repeat performance, and ultimately a better science output. As I said, the Scout program is also about accepting a control higher risk to small satellites. And I just wanted to give you an example of how we've established a very good foundation during the initial phases of the project, working with ESA. We started from a HydroGNSS statement of work, a set of tailored ECSS standards, and product assurance requirements. And we worked together with ESA to come up with a statement of compliance. And then through the negotiation phase, we consolidated a HydroGNSS tailored set of requirements. So really, we've been able to set the foundations for the future Scout programs as well, because we want to make sure we can deliver a good quality and reliable system, but yeah, being able to contain cost and schedule. So we've taken on board requirements like the space debris mitigation policy, but we've also been able to compromise and customize project reviews and documentation to make sure we can contain costs. So on this slide, you can see the diagram gives you an overview of the technical baseline. We have the ground segment in the green box and the space segment in the orange box. The system is designed to be flexible to support constellation if we wanted to add extra spacecraft in the system. And the satellite is based on the SSTL-21 product. As I mentioned, the core of the spacecraft is the science payload, which is what we called SGR-RAISE-Z, which builds its heritage on previous missions like TEC-DEMOSAT-1, Cygnus, and DotOne. But it also has the extra functionalities needed for HydroGNSS. And on the ground segment side, we have everything we need really to run the mission, from the Satellite Operations Center based here in Guildford at SSTL, the mission planning system, and the PDGS to process the data and make it available on the portal to the end users. On this slide, I just wanted to give you a bit of context in terms of where the HydroGNSS platform sits in the range of SSTL platform products. So you can see it's definitely in one of the most compact series of the full range, and it's part of the micro series with a mass that ranges between 50 and 60 kilos. So it is a compact design, but it has still very high capabilities. There is a dual redundant SSTL core avionics on board the spacecraft for a more robust system. The system is also configurable in orbit, so we can upload updated software once the satellite is already in orbit, including the science payload. And this is really a key element if we wanted to improve the science once the system is already launched. The satellite has 4 deployable solar arrays, which allows us to run the science payload at 100% duty cycle, so we can have a 24/7 data. But it's also flexible in terms of orbit LTAN, so we can launch the satellite LTANs. There is a high data rate downlink over X-band to download the science data, and it's running at 200 megabits per second. We also have a quite high capacity in terms of data storage on board the spacecraft with 500 gigabytes. There is a xenon propulsion system, which can be used for things like constellation phasing and collision avoidance firings. There is a 3-axis stabilized attitude control subsystem. That gives us the capability to potentially slew the spacecraft towards a specific target if we wanted to aim a specific area of interest on the Earth. So as I mentioned, the Scout program is about finding cost efficiencies wherever possible, and launch is a very good example. Historically, launch costs tend to be a fair portion of the mission budget. So we wanted to find a solution that was cost effective, and we managed to do that by picking up a launch opportunity on a ride share or a piggyback option. We've investigated different launchers, including Falcon 9, and we have selected Arianespace Vega C on a rideshare configuration. We are now under negotiations with Arianespace. Things are looking very positive, so hopefully we are very close to a contract signature. The rideshare configuration is also a good opportunity for launching multi-satellites together if we wanted to deploy a constellation. The reference orbit selected for HydroGNSS is a sun-synchronous orbit with an ALTA of 1030 and a nominal altitude of 550 kilometers. And with a polar orbit that enables us to capture measurements over high latitudes as well, so we can observe read-through products as well. Okay, going into the details of the HydroGNSS payload ConOps, we have 2 main modes in which the payload can be run. One is the routine capture mode, and in this mode, the onboard receiver computes the real-time geometrical tracking to center the measurements on the reflection. And in order to do that, we have an onboard digital elevation model, which is used for this application. There is also an allocation algorithm that is able to select the best reflections to track. And once those measurements are stored on board, they can then be downlinked over the X-band link to the ground station. So that's the main mode of operation, and it's the one running nearly 24/7. Then we also have a raw data sampling mode, which, as the name suggests, captures raw data from the receiver. But because this type of mode has a much higher data rate, we can only capture very short durations, a few minutes over a day. and so that's mainly focused for things like debugging operations or calibration campaigns. We mentioned quite a few times now why adding extra satellites could be beneficial for the mission. Obviously, one spacecraft is still sufficient to demonstrate the GNSS innovations like the dual polarization, dual frequency, and the coherent channel. So we can still have good products, good scientific products coming out of a single satellite. And the fact that we've selected a polar orbit gives a good coverage over 30 days. But as you can imagine, adding a second satellite can drastically improve the coverage. We can halve the days needed to have a global coverage. And the mean revisit time is also quite improved, going from 3.8 days to 2.9. So with that in mind, as you can imagine, with the second satellite, we could potentially monitor better some of the science products that have a more dynamic change. And there is also an opportunity to do some extra calibration activities using inter-satellite crossovers. So on this slide, it's just to show what I've just said. In this plot here, you see one satellite leaves quite a few gaps in the coverage, whereas adding in the second satellite fills in the gaps quite well. So in summary, the SSTL's experience is definitely a good fit for the Scout program. I dropped here some numbers just to give you an idea how many satellites we've built, how many launches. We conducted 40 launches over 12 different launch vehicles across 9 launch sites. We've developed and deployed 31 ground stations worldwide, and we have an accumulated operational experience of 500 years. And also SSTL's cost-based approach is definitely a good fit, again, in terms of containing costs on a mission. And the recurrent engineering cost is drastically reduced because of the way we work. All the cost efficiencies that we can achieve can still meet a very high performance system, and the SSTL-21 platform can support and accommodate a reflectometry payload running at nearly 100% duty cycle. And the system is reliable enough to provide an availability of the service better than 90%. And the system ultimately is also designed to be scalable to support future multi-satellite constellations for higher coverage performance. That would be it from me. Thank you very much.
Thank you, Serena. Are there any questions for Serena from the audience? Not at the moment, but I have a question, Serena. Can you tell something more about the pointing capability of the platform? This could be useful for future discussion, in particularly the possibility to change the attitude both in pitch and roll, and also the expected accuracy in attitude determination that can be important for the application and calibration.
Sure. So this platform is particularly agile, and we have the flexibility to be able to point the spacecraft nearly everywhere we wanted to. And we've also looked at maximizing the land coverage and checking what attitude point it could be the optimal fit to maximize the coverage. to put an offset a better coverage, because most of the reflections are not at nadir pointing. They come from an angle towards 30 degrees, and also some of the reflections, particularly the right-hand circular polarized reflections, are better captured if there is an incidence angle, if they don't come perfectly from nadir. So with all that in mind, we've decided to go for an off-pointing of the spacecraft in pitch. So that would be the nominal operating attitude. But as I mentioned previously, we have the ability to slew the spacecraft towards a specific target if we wanted to capture a specific area of interest. So the spacecraft is definitely agile, and it has a precise attitude control system on board with star trackers, which means we can achieve something like 0.5 degrees in terms of pointing knowledge, which is really the key requirement for reflectometry. Knowing well the attitude, the estimated attitude is quite key. I hope that answered the question.
Okay, thank you, Serena. There is a question from the audience. So very quickly, please. What technologies are going to be used in the PDGIS? Are you using COTS, as in the satellites? Are you using an in-house and ad hoc implementation?
So on the PDGS, we are developing that side of the system in collaboration with the science partners. You heard a few presentations by them this morning. And yes, we are developing it in-house. The processor, the level 1, level 2 processors are developed as software components by the science partners, but we will all integrate everything here at Guildford as STL to make it an overall system. And we are also using some heritage that we have from previous missions. We have the MERBIS portal up and running at the moment, so that's definitely a good piece of software that we're going to deploy and update for HydroGNSS. Does that answer the question? Hopefully.
Excellent. Yes. Thank you, Serena, for that insight into mission and systems of the HydroGNSS system. And thanks for the questions. So time to move on now, I think, to the next speaker. So next up, we have Reinhold de Vos van Steenwyk. He is a senior GNSS engineer, and he is the HydroGNSS payload manager. And he is going to be talking about HydroGNSS instrument summary.
Yes, thank
Reinhold,
you, Pete.
over to you.
Yeah, thank you, Pete. Can you hear me okay?
Yeah, you're good.
Good. Okay, good afternoon, everybody, and thank you for that introduction. I should just try and share my screen. Can you see my screen okay? Yep,
we can see you.
Okay. Okay, so yes, so good afternoon. I am Reinhold de Vos van Steenwyk, and as Peter said, I'm acting in my capacity as the payload instrument manager at SSTL for the purpose of the HydroGNSS mission. Let's try and move the slides on. Okay, so the HydroGNSS reflectometry instrument builds on the experience derived from long experience at SSTL in involvement in GNSSR from space, and it started all with the as we've heard this morning already, with the UK DMC GNSSR experiment. This was a pioneering GPS reflectometry experiment in orbit, which was embarked on the UK DMC imaging satellite, which was launched in with the embarked an additional downward pointing reflectometry antenna on the spacecraft that was connected to one of the spare inputs on the platform GPS receiver, which at the time was an SGL-10. And this was then paired with a data recorder that was able to capture some IF data output from the GPS receiver. With this hardware configuration, the UKDMC experiment collected around about 20 seconds of raw data, which was then downloaded for processing on the ground. And this represented the first dedicated GNSS reflectometry experiment in orbit. And over the course of that mission, around 60 data collections were gathered over sea, and spaceborne GNSS receiver remote sensing instrument. The SGRISI was developed with funding from, amongst others, the UK Centre for Earth Observation Instrumentation, and was a new GNSS receiver architecture based around a commercial FPGA with a Leon 3 processor core, and was paired with two front ends, 2112 front end chips. TDS was equipped. TDS1 was equipped also with a 2x2 spiral antenna array, which provided a high peak gain of around 12 dBi, with which to collect GPS reflections. A new processing core was implemented on an FPGA, which for the first time allowed for real-time generation of delayed Doppler maps in orbit. And this was the first implementation of the Zoom transform correlator architecture that we are still using today. Subsequent to TDS1 launch, exploitation in orbit was supported by funding from ESA, and a catalogue of data was made available to subscribers via the Merbis system that was mentioned by Serena earlier. TDS1 was very successful and collected many delayed Doppler maps from orbit. Research Institute, and targeted primarily gain delayed Doppler maps. The basic demonstration of GNSS reflectometry, and we did first times. DotOne, we're going to hear a lot more about DotOne in the next presentation when my colleague Jonathan Borenson will give much more detail as to the achievements of that study. But DotOne continues to be available as a hydrogen or GNSS instrument. HydroGNSS is better Doppler maps and coherent measurements at L1, L5, and across two different polarizations. The system includes a Zinc antenna for synchronizing to direct signals and a nadir antenna for receiving reflected signals. In the diagram, you can see that on the nadir side, we collect signals in the two different polarizations, and across two low noise amplifier modules. HydroGNSS capabilities. Primarily, it will be able to collect data tracking up to 4 reflections 24/7. That's 100% duty cycle, and it will simultaneously be collecting left and right hand polarized signals, reflections, and across the two frequencies L1 and L5. And it's in order to do this, it has 16 reflection channels, and it is also paired with coherent channels for each reflection. It is also capable of providing raw data collections for purposes of experimentation and research. This can be up to 15 minutes per day. However, it is limited by download capacity, and so it's restricted how much can be collected. It is also capable of doing routine operational calibration of the receiver chain to enable recovery of received signal power. This is achieved through the inclusion of a calibration load in the design of the low noise amplifiers. At its heart, it has a high performance Zinc FPGA with an ARM M9 core. And in case you were wondering, the addition of the -Z refers to the fact that it is this Zinc architecture that it uses. One of the key features is that all the software and gateware that is deployed on the HydroGNSS is uploadable in orbit via a dedicated TTC link from the ground, which enables operational maintenance of the payload and updates to the software and to the firmware. And in future, it's not precluded that new capabilities could be enabled in orbit in this way as well. So just to give a little bit of system context, the HydroGNSS is powered on the SSTL21 platform bus from the 12-volt bus. 3 LNAs are individually powered from dedicated supplies derived from that 12-volt input by the HydroGNSS. Routine operations and health monitoring and control of the HydroGNSS is performed over the CAN bus from the onboard computer, and a dedicated TTC link is available via the S-band transceivers for maintenance and updates of the HydroGNSS. Payload data is buffered in HydroGNSS onboard memory, and this onboard memory is periodically emptied by offloading to the platform data recorders prior to payload data being downlinked over the ground stations by the X-band transmitters. The core functionality for reflectometry is implemented, as I said, on the Zinc. The Zinc implements all the navigation correlators, the zoom transfer correlator blocks, as well as the coherent channels. It provides navigation capability, reflection allocation, and produces all the ancillary data files required for the processing of the payload data. And also, it is flexible enough to be able to be reconfigured in orbit. Below you see a picture of our breadboarding development environment on a Xilinx development board. Moving on to the low noise amplifier module design. The low noise amplifier is very key to the overall performance of the system. The design is for a high gain, low noise figure, low noise amplifier to preserve the weak signals, the weak reflected signals as best we can. It is designed to, and as I mentioned, it incorporates a calibration switch on each of the receive paths using a blackbody load for routine calibration of the receiver gain and noise figure. It also includes a rate for changes over temperature. And the module is also equipped with a cavity filter, which provides robust mitigation for out-of-band interference, while also ensuring minimal losses. Noise Amplifier has been demonstrated in prototype testing, and the performance is looking very good. And we are currently in the process of producing our engineering models for further testing and qualification. And the other, obviously, key aspect for the design of the payload instrument are the antennas. The HydroGNSS antennas is a new design, which we call the dual all-metal patch antenna, and it's being designed to provide high efficiency for signals received in dual polarizations and across the two frequencies of interest. The design uses stacked resonant disks, and a complex feed network accommodates the dual frequency, dual polarization requirements, while also trying to minimize losses as best we can. For the Zinc antenna, we use a single antenna, providing a medium directional gain and good efficiency. For the Nadir antenna, we employ a 2x2 array to provide increased gain at bore site, which helps us to receive the signals better from the reflected signals better. The design is as optimized as it can be for providing gain, whilst also maintaining a relatively wide beam width to maximize the number of trackable reflections within the footprint of the antenna. So this slide shows some of the simulated antenna patterns. These are the ones that we are working with, and we are achieving a very good peak gain performance of around 14 dB for the L1 frequency, with around 45 degrees full beam width for the 6 dB beam width. And for the L5, it's around about 12 dBs, though we are still investigating further optimizations and ways in which that could be brought up further as well. Commensurate with that, the beam width on the L5 is around about 55 degrees. So this is just an illustration of the prototyping activity for the antennas for the new design. We've manufactured a prototype antenna which has been tested and which has successfully demonstrated that the simulated performance is proving to be possible in reality as well. The feed network and the mechanical design of a full EM antenna are now in progress. Okay, so now just to conclude, to summarize, HydroGNSS payload instrument design builds on the strong heritage of it at SSCL in GNSS reflectometry built up over many years. The design of the payload has been optimized for the requirements of the mission and will enable new measures. The SRSZ leverages the high data processing capabilities of modern FPGA-based designs. The LNA is optimized for low noise figure while still offering calibration and interference mitigation. And the HydroGNSS antenna design is optimized for high gain over L1 and L5 and for dual polarization, while still maintaining a wide beam width to optimize the number of trackable reflections. Prototyping and engineering model design is well underway for all elements of the payload SSCL. That is the conclusion of my presentation. Are there any?
Thank you, Reinhold. So let us see if there are questions for you. Couple minutes, I would like to ask something. If you can explain better which is the amount of flexibility that we have in selecting the channels. I mean, we have 16 channels. Can we change as we want? For instance, just to give you an example, can you use all the 60 channels, only L5, just to make myself clear?
Yes. At the moment, it's not completely precluded. Reconfigure to a certain extent the allocation of little reflections.
Any other question? If not, probably Peter, we can move to the next presentation.
Yeah, excellent. Thank you, Ray, for that dive into the instrument. Very interesting stuff. I'm sure everyone got a lot from it. So moving on now. So our next speaker is Jonathan Rawlinson. He is a senior GNSS engineer and GNSS R payload technical lead. He's going to start on the HydroGNSS precursor. Jonathan.
Lovely, thank you very much. So yes, my name's Jonathan Borenson, and yes, I'm here to talk to you today about the work we've been doing on DotOne. So DotOne, as you probably heard beforehand, has been used to demonstrate some of the new and important activities that have been happening at SSTL since Tech Demo Sat 1. So I thought you'd take you through the story of DotOne. And is that working? Is that changing slide? No, it's not. Aha, there we go. So yes, DotOne. DotOne is a 17.8 kilo technology demonstrator satellite. And this is an SSTL mission, so an SSTL owned mission with the full aim to test and verify our new onboard architecture and avionics suite, which is the core DHS. So this is a unit that contains all of the core avionics for our future SSTL satellites, and this was the first flight. DotOne had two primary payloads, one being a Raspberry Pi camera and the other being a radiation monitor. But at a very late edition, we added a 8 dBi LHCP GNSS L1 antenna for the concept of demonstrating GNSS reflectometry as a secondary payload on a satellite. So yes, overall, DotOne SSTL mission, but this is a microsatellite. This is not a very big satellite. Oh, no, that's not working. There we go. So the core DHS has, as I said, numerous components on it, but two of interest here being our SGR LIGO, which is the onboard platform GPS receiver, and then the Zinc data processing unit, or DPU. So on the left-hand side here, you can see that the data is the front-end data is routed from the SGR LIGO front ends and is routed across the core DHS to the bottom right-hand side, which is the Zinc DPU. The SGR LIGO is a single frequency GNSS receiver, but it has two front ends. Nominally, for most missions, you'd have one antenna pointing up and one antenna pointing down for navigation. But in this case, we attached a normal receiver antenna on the zenith, but then, as I stated earlier, attached a nadir facing antenna for reflectometry. The SGR LIGO is a flash-based FPGA, meaning it cannot be reprogrammed in orbit, although we can update our application software. And then, as I said, we transport this raw front-end data across the core DHS to Zinc DPU for experimentation at this point. So for the, as Ray discussed in the previous presentation, for the Zinc, both the VHDL and software are reprogrammable in orbit, as it's a RAM-based FPGA. And the Zinc is significantly faster clock and consequently draws much higher power than the SGR LIGO. As part of this study, we took the GNSS software and VHDL from the original SGR Resi and ported it across to the core DHS. So DotOne, it was launched in July 2019 into a 530K orbit, sun synchronous, and it was one of 34 satellites launched on a Soyuz. So it was part of a it was a piggyback payload on one of the Russian weather satellites. We successfully commissioned DotOne, and on the right-hand side here, you can see a photo that was taken by the Raspberry Pi, a nice photo of Italy there. And we also recorded some video as well. And then after this, there's a YouTube link there if you want to see some live, some video from DotOne. So overall, at this point, DotOne was a functioning satellite, but importantly, it only had a reflectometry attached. It did not include the reflectometry functionality at that point. So in conjunction with European Space Agency, we worked to adapt DotOne into a reflectometry mission. So this was the extension of an earlier study known as Aurora, where we were looking at reflectometry and radio occultation. And the aim of this study was to show that reflectometry is possible to be integrated into a small satellite. So as I said in the previous slide, we brought across our existing technology and IP from the original SGR Resi to our new processor. So we moved all of the zoom transform correlators and navigation correlators into the programmable hardware, and also moved across our software to a new operating system as we had a different baseline on DotOne. We tested our software and configuration on the ground. So we had an engineering model in the lab, and we made sure it was thermally cycled and thoroughly tested before flying it on DotOne. And then we uploaded these files to DotOne to enable the capability. And once again, to emphasize, this was done long after launch. When DotOne launched, it was not capable of doing reflectometry, but this study was to enable that. So DotOne has a number of differences when it comes to comparing to HydroGNSS. For example, DotOne has a significantly lower gain, but a wider beam width on its nadir-facing antenna. So it's roughly 8 dBi versus 13.8 dBi at L1. Our field of view is larger, so if we can see signals significantly off-axis compared to Hydro, and we have less, and due to this lower antenna gain, we have less sensitivity to our astral uncertainty. So there are a few. There's one minor advantage of DotOne. We are at a lower altitude, so by definition, our reflected signals are going to be slightly stronger at that altitude. But we also have a number of limitations. One being the low data rates. We are limited to a standard S-band telemetry and control link. We don't have the X-bands like we have on HydroGNSS. We are limited to a single frequency and a single polarization, and we have no onboard calibration facilities. So the steps that we took to get DotOne working in reflectometry mode was to start off by, can we actually even get a GPS position using the Zinc? So one major challenge that we had to overcome was confirm that the RF samples passed from the SGR LIGO to the Zinc were correct and stable enough to use for reflectometry. And in July 2020, we obtained our first GPS position fix from the Zinc. So this proved that the signal processing chain between the SGR LIGO and the Zinc was stable, and gave us confidence that the DotOne platform was suitable for reflectometry. And on the right-hand side there, you can see the ground track of our first ever Zinc-based positioning on DotOne. So a nice little track over there of the Pacific and then going over Antarctica. And yes, this was the first major achievement of the DotOne project. Secondly, we had to try and get DDMs going. So the original SGR Resi was a single frequency. The heritage from the SGR Resi allowed us to bring across these GPS L1CA DDM production, so the standard course acquisition code. And in August 2020, we had successfully brought across this functionality and obtained our first DDMs. So our first test allows us to collect 40 minutes of DDMs. Our DDMs were allocated as per TDS1, i.e. Looking at the highest antenna gain at a certain point and ordering our reflections in that manner. So 1 year after launch, DotOne started taking Doppler delay maps, and this was a major achievement. And on the right-hand side there, on the top right, you can see some nice ocean DDMs from GPS L1CA. And on the bottom right, you can see the associated specular point tracks for those reflections. So once again, a nice track over the Pacific Ocean. But this was, yes, this was amazing. We managed to get our first GPS L1CA DDMs from DotOne. In addition to collecting DDMs, DotOne is also able to record raw data samples. So also in August 2020, we were able to record 1 second of raw data. So this is both the zenith and the nadir channels from DotOne. It's noted that this is significantly less than HydroGNSS and also significantly less than TDS1, primarily because we are significantly limited by our S-band downlink rate. So as I said before, we only had an S-band transmitter, and this was primarily designed for telemetry and control. It was not designed for payload data. So this was one of the main limitations here for collecting raw data. But from the collection that we did in August 2020, we used our software receiver to collect Galileo, Beidou, and other signals from the Zenith channel. And overall, this gave us confidence that DotOne was not only suitable for GPS reflectometry, but also potentially Galileo and other signals using the DotOne platform. So the next step was, can we get Galileo working? So in December 2020, DotOne obtained its first multi-constellation PVT fix. So this is combining both the GPS L1CA and the Galileo E1B signal. And data from this test allowed us to firstly improve our Galileo software and get a better understanding of what it means to operate a multi-constellation receiver in preparation for doing multi-constellation reflectometry. And initially, for simplicity, we only used the only half of the E1 OS signal, which is the E1B signal, and starting off using 1 millisecond integrations, which is the same that we use for GPS. And on the right-hand side there, you can see this is an output from one of our receiver windows, and you can see on the top there that you've got a nice load of Galileo signals being tracked. So yes, so this was paving the steps to doing Galileo DDMs in orbit. So then, the most exciting bit is in March 2021, we obtained Galileo DDMs. So we collected a significantly larger, at this point now with significantly optimized operations, so we can collect significantly longer lengths of DDMs. But yes, so on the right-hand side there, you can see some examples of some Galileo DDMs with the green star indicating Galileo and the red star indicating GPS, as we'd also updated the algorithm so that it can select the best reflection, not necessarily limited to the best GPS or Galileo reflection. And on the bottom there, you can see that we've got a nice strong double peak there. You can just about see the two Bock ACF peaks there. So overall, this was amazing with that. So this is the first Galileo DDMs that we've produced at SSTL and proved that the DotOne platform is suitable for this task. So yes, so on the top right here, we have some ICE DDMs. So you can see a nice strong on the most, there's you can see a nice strong ice reflection there from Galileo. And then on the bottom there, you can see on the bottom right-hand side, you've got some ocean DDMs from both constellations. And you can see that classic arc shape over the ocean. So we've performed some very initial analysis in conjunction with the NOC. Who you'll be hearing from, or who you heard from earlier. So the early analysis from the NOC shows that there is a relationship with wind speed from the DotOne DDMs when compared to ERA5, which shows a clear SNR to mu10 relationship, which is very similar to TechDemoSat1. So overall, this is indicating that the data we're getting from DotOne is very useful data. And then when looking just at the Galileo signals, it shows that they also show a good relationship with the wind speed, although the SNR is weaker as expected due to the limitations of our initial implementation, as we are only using half the signal at the moment. And on the right-hand side here is just a nice plot of the ice edge over Antarctica. And you can see there there's quite a clear outline of where the ice is, and this aligns pretty well with some of the other data sources available. But overall, it's showing that DotOne is producing useful data, and watch this space for future presentations on how this compares to other missions. So current status of DotOne and what we plan to be doing. So DotOne operations continue long past its design life of 1 year. And I happen to be looking at the ground station at the moment, and it happens to be doing a pass right now. Between May 2021 and August 2021, we were operating in a regular operating mode and achieving approximately 6 hours of DDMs per week. So 6 hours of multi-constellation DDMs per week. In conjunction with the Surrey Space Centre, with Lucinda King, and we've implemented an onboard digital elevation model. So this allows us to correct our speculative point positioning over land to help with retrieving land measurements. Our Merbis software and level 1B data structures have been updated to account for the new style DDMs, and our aim is to release our DotOne data in due course via Merbis as part of this study. We're aiming to improve the use of our Galileo channel, including using the full signals, because currently we are only exploiting half of the Galileo E1 OS signal. And as of February 2022, DotOne has been returned to proper full GNSS operations again, and is acting as a valuable demonstration platform for the HydroGNSS mission. So overall, we have successfully moved GNSS reflectometry onto our 18-kilogram DotOne satellite as a secondary payload. So yep, it's this was not the primary payload when DotOne was launched. The core DHS is the heart of all of our future SSTL missions. So there's potentially there was a potential to deploy reflectometry onto many future satellites at a low cost. Our GNSS reflectometry has been upgraded to process both GPS and Galileo, which is very valuable for HydroGNSS. And overall, DotOne development is a valuable technology stepping stone for HydroGNSS. But it is noted that HydroGNSS does provide significantly more additions, including, as discussed earlier, dual frequency, dual polarization, and other options like that. So thank you very much. Any questions?
Thank you, Jonathan. There is a question from Jadir, asking whether the DDM from GPS Galileo were collected in dual frequency or single frequency mode.
So DotOne is only capable of single frequency, single polarization operations. So these DDMs were only from L1.
Okay, thank you. Any other question from the audience? If not, probably I have time for a quick question. I'm just wondering what, in addition, what DotOne can do in support of HydroGNSS. For instance, is it possible to use DotOne to verify the effect of changing the pointing? Also, for assessing the effect on the POD of changing pointing. And another possibility is also trying to test different coherent integration time. Is there room to do this type of experiment with DotOne?
So we are currently in discussion with ESA on extending the current study to investigate just what we're talking about. So yes, we're looking at having a CCN to investigate different coherent integration times and how we can overall improve the Galileo product. Currently, I'm not best placed to comment on DotOne's AOCS abilities, but it's that the AOCS platform on DotOne is significantly more basic when compared to HydroGNSS. So I would doubt that we can do as advanced things that HydroGNSS can, although I will get back to you on that. And yes, we are. And also, in addition, we're looking at, as part of this, potentially as part of this CCN as well, we might be able to demonstrate, or this CCN or future CCNs, we might be able to demonstrate some of the newer HydroGNSS functionality in a very basic sense. For example, there's the coherent channel, which was discussed earlier by Estelle, who where we might be able to utilize DotOne to see what this data could look like as just a first look, and other things as well. So yes, the answer is yes, we can investigate some limited subsets of HydroGNSS functionality.
Okay, thank you. Any other question? Okay, so I have one more because it's we have still 2 minutes, but just to simulate the discussion. What about signal to noise ratio with an antenna of only 8 dBs, especially over land? That is my major interest.
So we are getting reasonable signal to noise ratios. We haven't yet completed the analysis, so I can't say for sure at the moment. We haven't completed the full analysis of our data sets that we generated. But so far, over the ocean, we're definitely seeing reflections, as on this final slide. You can see that there's a nice set of ocean reflections there. But that's still one question we're asking ourselves. And at the conclusion of this study, we hope to answer that question.
Thank you. I mean, now it's time to move to the next one, Pete.
Excellent. Thank you, Mauro. And Jonathan, thanks very much for that really interesting deep dive into DotOne and its capabilities and its future, hopefully, as well. So last presenter for this session we have Martin Unwin, and he is a principal GNSS engineer at SSTL. He's going to be telling us all about HydroGNSS measurements and the calibration approach. Martin, the floor is yours.
Okay, can you hear me and can you see the slide?
Yes, to both.
Okay, thank you. I'll just move this out of the way. Right. So we've heard quite a bit about the mission, and then I'm going to be talking a little bit more about the measurements and some of the, we've heard a bit about the calibration, so we can talk a bit more about that. So in terms of the progression of measurements, since the first experiment that we put up on UKDMC, that was, as we heard, that collected 20-second of raw sample data, and it was limited by 128 megabytes. And it was, we worked with a software receiver on the ground in order to recover the signals, and it took a lot of work from my colleague Scott Gleason, who did much of the work on recovering the signal. But we found that we could pick up collections. This is what proved that we could pick up delayed Doppler maps over all possible surfaces, over oceans, land and ice, in about 60 collections we took over its lifetime. And then we moved on to Tech Demo Sat 1 with the SGR Resi, and that actually processed the delayed Doppler maps on board. So instead of taking hours to download a few seconds of collections, this could generate data and more or less keep up with downloading it in real time. So this is every second for delayed Doppler maps, and my colleague Phil Jales worked on that with our team. And this was a massive step forward because we could take thousands of reflections, millions of reflections, compared to what we had on UKDMC. We still had the capability of collecting raw data typically for about 2 minutes at a collection. And so we did have the ability to reprocess on the ground with the software receiver. And that SGR Resi instrument was the one that was provided for Cygnus. And Cygnus had 2 antennas, but it's still limited by 4 reflections, GPS, left-hand circular polarized. So then the next step, as we just heard from Jonathan about DotOne, in some ways it's a much more restrictive platform. Only 18 kilograms, and this was a secondary payload on an 18 kilogram satellite. So it really was showing that it can be done in the tightest of situations. But we were able to demonstrate continuous delayed Doppler maps collected from L1, but we've added Galileo to the collection now. We're still working on that, but while we could collect the data continuously, there was a downlink limitation from the platform, which means that we could only log 6 hours for every 24 hours roughly, although there is more that we can do to window and compress the data and get it down to a continuous collection. So that's still work in progress. We also were able to collect raw data, but that's quite a job. There's limitations stopping it at about 6 seconds. And then there's downlink limitations. The extreme limitations on DotOne means it takes days to download such data like that. So now that puts the context for HydroGNSS. So this is the SGR Resi instrument, which we've heard about, and it's ported and upgraded into a new hardware. And that will be able to collect continuously from 16 channels. And these 16 channels can be allocated to dual frequencies, dual polarization, delayed Doppler maps, plus it has coherent channels running at a fast rate. In terms of raw data, we expect to typically collect 60 seconds of data at around 50 megahertz with the different measurements, dual frequency, dual polarization. But we do have a very large capacity on the satellite, so we are actually able to store up to 15 minutes of raw data collection. And you've seen this diagram before, but just to revisit it. So the established GNSS reflectometry approach is to use incoherent delayed Doppler maps from GPS at L1 at 1 Hertz or a bit faster at 2 Hertz. And that was demonstrated on Tech Demo Sat1 and on Cygnus, and so that's using diffuse unipolarized signals. But there's other aspects of the that could be collected and exploited from reflected GNSS signals. And with HydroGNSS, we're aiming to tap into those. So first of all, we're adding the Galileo signals, and we've got the first demonstration on DotOne for that. That adds increased coverage. So for the same antenna footprint, we will get double the number of measurements roughly. The Galileo signals are slightly different to the GPS L1. They're double the bandwidth, and they've got longer codes, so there's more potential for increased coherent gain and rejection of the cross-polar spurious measurements. Then we have the polarization. So we have left and right-hand circular collections of delayed Doppler maps. And that, as we've heard from the science presentations, could separate out soil roughness from the soil moisture. And there's also the effects of vegetation that it may help to add a new measurement. And then we're adding the coherent complex channel. So that's targeting the reflections which has been identified there, that often you pick up these more coherent reflections off the surface, and that channel is targeting those. And that allows, where there is a flat surface, it allows us to access higher resolution. And it also means that we can apply more processing gain. So we may be able to pick up weaker signals from underneath forest canopies. And then we're adding the second frequency, which is another exciting new step into the unknown. I mean, the characteristics of this signal is that they're much wider band. So in principle, they can target smaller features. But they're also because they target smaller features, you've got less power reflected back. So it's very exciting. I think there's a lot of people wanting to see what the L5, E5 signals are like. There is potential for higher resolution and also for detecting different kind of characteristics on the ground. And these new measurements are being backed up by new simulations. We'll hear from the end-to-end simulator in due course. So here's a table showing the different measurements that we have. So the red stars indicate the measurements that we've got from TDS1. So we have L1 band non-coherent delayed Doppler maps from TDS1, and we also have black body measurements, and we also have L1 band sample data. So you can see the green stars show all the new measurements that are being added by HydroGNSS. So we are adding the opposite polarization for GPS. You can see the column to the right, we've added Galileo, although that will just merge together with the GNSS signals, but it does introduce a new dimension that we've got these Galileo left-hand and right-hand circular measurements, as well as the GPS left-hand and right-hand. And you can see it's not only L1, we've also got the L5 non-coherent delayed Doppler maps. And for each of those, we are allocating coherent channels too. And the black body loads will be applicable to both L1 and L5 bands, both polarizations. And then we have sample data from the L1 left and right, and the L5 left and right. So you can see there's a great deal more measurements that are potentially possible from HydroGNSS. So the approach for the new measurements, well, the GPS and Galileo L1E1, we are using the zoom transform correlator that we developed during the time of TDS1, and that will be used to generate the delayed Doppler maps for GPS and Galileo. And they have similar adjustable settings, but we will be investigating the optimal settings to get the best signal to noise. We're adding Galileo signals, and we're looking at increasing the signal to noise by combining the two halves of the signal. So Galileo E1 transmits a pilot signal and a data signal, and we're looking to see whether we can combine the two of those. And using longer integration times will increase the signal to noise, but that means we need to account for the secondary and the data bits, which is one of the challenges we're tackling at the moment. The coherent channel is, in effect, it's a split off from the ZTC at the very basic level, a single pixel located at the peak, and it's complex values, so it's amplitude and phase, or in the form of in phase and quadrature. And the dual frequency and dual polarization it calls for higher sampling rates. So we're using higher sampling rates throughout to deal with the wide bandwidth. And we're using the same ZTC approach for the L1 and L5 bands. And the delay Doppler maps settings we expect to optimize according to the code. So it will be different for the L1 as it is to the L5. And then the operational mode will normally be collecting collections, continual collections of delay Doppler maps and occasional collections of the raw IF samples. So these measurements feed into the data level. The primary data type is the continuous delay Doppler maps, which we've labeled level 0B, and those will be fed into the level 1 processor, which level 1A is when it's the data is collated together, and then level 1B is when the derived corrections are applied. So these are for correcting for radiometric corrections and transmit powers, and then they're passed on to the level 2, and those are the climate variable products, things like soil moisture, etc. And we're reusing a TDS1 Merbis processing architecture as the starting point, and then plugging in new processing modules. And we're expecting the inversions, we're expecting them to evolve over a period of time with new measurement types, and we expect the mission to evolve with time as we discover more about the new signals that we are collecting. So a few words about the calibration approach. Firstly, there's so much that has been learned from TDS1 and from Cygnus missions that can be applied to the L1, and it should apply to E1 as well, left-hand circular polarized, and we think it will apply to the coherent channel as well, largely. So looking at the picture, what we're trying to do is to measure the reflection coefficient, whether it's in the form of reflectivity or a radar cross-section. That is what we're trying to measure. It's the surface reflection, which is the reflected signal over the incident signal. So there's two halves to this. One is trying to measure the reflected signal, and the other half is then trying to estimate what the incident signal is. And this has many factors, which I've tried to show on this slide. So the transmit power makes a difference, and how that varies with time. The transmit and receiver antenna patterns and what angle it's picking up the signal. The antenna noise is the noise that is picked up by the antenna, which could be thermal noise, but it could also be artificial noise. And so there tends to be quite a bit of variation in the antenna noise. And then there's other thermal effects as the receiver gets warmer and colder. And so we're using a number of techniques. We've heard from Nock earlier, from Giuseppe, about using the ocean as a target, but we can also use the Antarctic as a target to help fix the calibration, radiometric calibration. And we have black body load on board, so we have different ways of correcting some of these parameters. And just a few more words about this. So approach to measuring the receiver power, we have the noise figure and the system gain, which will vary as a function of the LNA temperature and other temperatures on board the platform, the instrument. And these can be verified against black body load measurements and the Antarctic target to make sure that we have the correct equations. And then there's other second order effects such as bit distribution under consideration, and this has been something that Cygnus has been working on in the latest version 3.1. We're still looking at whether we will be applying bit distribution or whether we can actually still operate it. We may be able to operate in automatic gain control and then read back the gain control. So we will certainly be taking that into account. And then, as I said, the radiometric corrections apply to both the coherent and the dual frequency. Then the other half is trying to estimate the transmit power. When we first started doing reflectometry, we assumed that transmit power was constant, which was a good start, but it soon became clear that it's not constant. And we need to allow for the different GNSS blocks, the different antenna patterns, and different transmit powers, and even to the point that some transmit powers change with time. So the approach that we've used very successfully with our partners in NOC has been using ocean reflected signals. So using large periods of collection can really home in and fix the patterns and powers from individual satellites. But the other approach is why we supplied blackbody loads with the low noise amplifiers that we supplied on TDS and to Cygnus, was to allow us to calibrate the zenith signals as well. And we can use the same approach to correct for radiometric gain that we do for the nadir, so that then we have a chance of taking accurate measurements from the zenith antennas. So we can map out the zenith antenna on the receiver, and then the method that Cygnus has been using recently is to use the GNSS antenna map and adjust from the receive vector to the specular point vector to get the most accuracy. And this is primarily applying to the L1 signals, but there's challenges in the new measurements. We're talking about second frequency, and we're talking about the opposite polarization as well. And these are new areas. A little bit more about the GNSS antenna mapping, pattern mapping. On another project that SSTL was involved in, we flew a GPS receiver on the Galileo demonstrator satellite, GOVA. It was launched in 2005. That carried a GPS receiver which achieved the first position fix above the GPS constellation. So it was at an altitude of around 24,000 kilometers in medium Earth orbit. And it was using GPS signals from the far side of the world, blocked by the Earth. So we picked up the signals round the rim, and the diagram on the right shows what we saw with our GPS receiver. So we worked with ESA to map out the GPS antenna pattern and the side lobes that were transmitted beyond the Earth using the spaceborne GPS receiver. To do this, it was necessary to model the GPS satellite yaw rotation to observe the variation in the azimuth pattern. And as you can see, it's a massive variation for the side lobes, and it's different from one GPS block to the other. So we used that work, and then we adapted the tool so that we could do it for using GPS receivers in low Earth orbit to map the patterns facing the Earth. And there's a map there on the bottom right, and you can see that there is much, much less variation in azimuth. It's mostly a variation with off-pointing, but there is some variation in azimuth. It's still visible. So this antenna amplitude mapping, we think will be valuable for the GNSS reflectometry. It means we can use it to predict the power in a certain direction, accommodating off-pointing and azimuth angles. And the same approach can apply to both GPS and Galileo. And this will be useful for both ocean reflected and direct signal-based calibration. So the new measurements will be available from HydroGNSS. We'll be using advanced algorithms. Initially, the data will come from the end-to-end simulator and extrapolated from airborne campaigns. The baseline inversion will tend to use the signals that we know and we can quantify best, but the advanced techniques will be using some of the new measurements that are coming along. So we've heard a bit about this from the other presentations, so I won't go into the details here. And then the roadmap towards the users is that when we're in orbit, we'll be calibrating the L1B, and we'll be validating each level 2 product tested. And we're developing plans with our science partners about how we're going to do this validation. And we are trying to set the correct level of goals so that we can do the preliminary validation after 6 months to show that we've achieved our goals. And then users will be able to have access to the level 1B as well as level 2 data with the latest release calibration applied. And finally, we've still got work to do. We want to uncover more about the new reflection measurement characteristics. And there's a lot of interest in the new measurements that are going to be coming down. We've got good confidence with the L1E1 LHCP measurements. And we've got growing confidence with the coherent channel from the raw sample data, but there's still some work to be done to show that we can, how we're going to handle the coherent channel, and maybe DotOne will be part of that picture. We can't use the same approaches for calibration of all the other new signals. So the reflections of L5E5 signals off the ocean may be weak and or intermittent. That's still an area of investigation. And currently we have no direct acquisition of L5E5 signals on the satellite platform. So the direct approach cannot be used. The cross-calibrated direct signals, the cross-coherent polarization signals are expected to be very weak. And so the opposite polarization on the satellite is going to be difficult. So we are investigating these methods of calibration for the new methods. We're initially starting with model-based approach, and these models will improve with experience. And maybe observatories on the ground may be able to improve models, but we are hoping to collaborate with other campaigns, land and air, to validate our approaches and improve the calibration. So it's still quite early days. It's an exciting time, but there's plenty of work to be done. And for reference, I've added the references at the end, and that's the end of my talk.
Thank you, Martin. Interesting. And there is a first question from the audience. Why do you want to calibrate the zenith antenna power, as it will not have much antenna noise since it's collecting the cold sky noise?
Okay, well, the reason why we want to calibrate the zenith antenna is because it is part of the scheme to measure the transmission powers of the GNSS satellites. And that's proven to be quite important because, coming back to this diagram here, we can measure the reflected signal accurately, but we need to infer what the incident signal is. And it's more variable than you might think. So by using the signals from the direct antenna, we have one method to calibrate that. The other method, of course, is to have a good model of what the transmit powers are from the previous several months of operation over the ocean. So we have two approaches to try and measure and model the incident signal, but the direct antenna pattern is needed in order to use the direct signals for that calibration.
Okay. Then one more question. Is airborne ground penetrating radar an option to validate soil moisture data? My personal opinion is yes, but of course we have to collect data in situ. So this is an effort that is not included in this project at the moment. But Martin, please.
Yeah, no, I think the when it's coming to the validation campaign, then it's all hands to the deck, and we have to be practical because it's a low-cost mission, and we're time limited, so we have to try and use our resources in an efficient way. But I think I would probably speak for you, Mauro, by saying we're open to collaborating with other people who may have different methodologies as well. We can always talk to other people about the validation.
Yes, of course. Two more questions. I don't know if we have time. I will put both together so you have you can answer quickly. That is, one is about how much link margin is expected in case of L5E5. And the other one is, could the dual frequency measurements be used to study ionosphere?
Two very good questions. The link margin L5E5 is a very, very hot topic. And we have members of the Science Advisory Group and members of the science team discussing that at the moment. And it boils down to the fact that if the surface is rough, then we think that the signals are going to be very weak from the L5E5. They may be, that's what the reflection, the simulators indicate. But when the surface is flat, then they will be very strong. So the question is, what will land look like where you have strong reflections off flat surfaces and weak reflections off rough surfaces. It's going to be a mixture. And I think that's very exciting that it's going to look different to what we see in the L1. So the link margin is a difficult one to answer for that reason. Sometimes it's going to be weak, sometimes it's strong. Most of the time it's going to be a mixture of the two. So that's where we are. And the other question is about measuring the ionosphere. I think technically there's more directions we could go in, and we have to limit how much we do, but technically our instrument would be capable of taking measurements of the ionosphere by reflections off either off the ocean or off the ice. I think you need to have the dual frequency, so that there could be ways forward. I think there's a lot of people doing work using radial occultation and also the grazing reflections, which are probably sooner able to get to the ionosphere. So I don't see that in the short term with the work that we're doing. But technically, there may be a route towards that in the future.
Okay, thank you, Martin. Peter, probably it's time to close this session.
Yes, thank you, Mauro, and thank you for that, and thank you, Martin, for that really excellent talk and answering the various questions. So yeah, Mauro, thank you very much for coordinating all of the questions. Been a pleasure co-chairing with you. So yeah, that draws to conclusion, session 3. Thanks everybody. Hope you everybody got a lot out of that dive into the mission details. Thank you very much.
Thank you.
Bye bye.
Bye.